Hello, in this lecture we want to cover sections 11.4 and 11.5 about comparison tests. In this part we're gonna learn how to deal with series whose terms are not necessarily positive, okay? So of particular importance is the form of this alternating series whose terms alternate in sign. So we're gonna see that this alternating series has the terms that alternate positive and negative consecutively, one after the other. Here is an example in which I have 1 minus half plus 1 over 3 minus 1 over 4. When I look at this example, actually the form, the notation could be written in the form negative 1 to the power here n minus 1, because I'm starting here when n is equal to 1, I have a positive value. Definitely هتديني at first positive first term this power. Okay, the terms or the general term actually is changing with 1 over n, so I can look at this series actually in this general notation. Also another example, if my example starts with negative مثلا values, say مثلا negative half plus 2 over 3 negative مثلا 3 over 4, I have here alternating between positive and negative signs also. So when I look at the pattern here, I'll see that I have negative 1 to the power n now, because the first term is positive, and the terms change according to the value of n as n over n plus 1, right? Where n changes from 1 to infinity. But these two examples actually are examples of alternating series in which the nth term of the alternating series is of the form, when I look at my nth term in the first example, actually an is the term negative 1 power n minus 1 for 1 over n. For the second one, an actually is the term negative 1 power n phi n over n plus 1. Any series that can be written in the form an in which I have a value a plus or minus اللي هي term اللي فيه negative sign and a positive term is an alternating series, where bn definitely is the absolute value of the nth term and is always positive. Similarly here it could be written as negative 1 power n times bn, in which also bn is the absolute value of my terms. Now if we looked at again at our alternating series and asked if this series is convergent, actually this specific series, yes, it is convergent, because I'll notice that the partial sum, when I say S1, which will be equal to B1, which is a 1, okay, this is my S1, and the partial sum S2 will be the B1 minus B2, I'm going to subtract a value that is less, B2 here is less than B1, then definitely I'll be alternating to S2, okay, as a partial sum will be less than S1, and so on. S3, I'm going to add up B3, I'll arrive at this term S3, which will be less than S1 but greater than S2, and so on and so on, with my partial sums will be oscillating and will be converging towards the sum the sum S. This will only happen if two conditions are satisfied, and we will arrive at the following test. Actually, it can be seen from this figure that these conditions actually to have a convergence to this, as one of them is that the term bn must go to 0 as n tends to infinity. This is a necessarily condition. The second thing, the terms bn must be decreasing. I must have that bn plus 1 is less than bn. But the bn's must be a decreasing sequence, and actually they must decrease towards the value 0 in absolute value. Okay, then the series is convergent. Thus we arrive at this test. We call it the alternating series test, and it applies only to alternating series of the forms that we define. The first condition, definitely I must rewrite it in the series in this form. An, I must write it in as a product between the plus or minus and times a positive value. But the first condition, let's call it 0 condition, is that the bn's must be positive. The second thing, to make sure that the bn's is a decreasing sequence. If it's decreasing for all values of n and a limiting value goes to 0 as n tends to infinity, the test applies, and I have a conclusion here for my alternating series that it's a convergent series. If one of these conditions does not apply, then the test fails, or I cannot apply this condition, as we will see from our examples. Now, if we go back to the example we started with, 1 minus half plus 1 over 3 minus 1 over 4 and so on, we know that this is an alternating series written in the form negative 1 power n minus 1 phi 1 over a 1 over n. Okay, let's check if we can apply the alternating series test. We're dealing with bn, which is equal to 1 over n, definitely is positive, and the first condition that bn plus 1 is a decreasing sequence is satisfied, because I must mention why, and because I know that 1 over n plus 1 definitely is less than 1 over n. Here the denominator is bigger than the term is less than 1 over n. The second condition is the limiting value of the bn, or the terms bn as n tends to infinity, is the limit of the 1 over n as n tends to infinity is definitely is a 0. I must do all these checks to be able to apply the alternating series test. So my conclusion now from this analysis, that the series is convergent by the alternating series test. Okay. Now we need to estimate the sum. A partial sum Sn of any convergent series can be used in approximation to the total sum, as we did before. But we're going to approximate the sum with a sum partial sums type. But this is not much, as we said, use unless we can estimate the accuracy of the approximation. The error involved in this approximation is as we did before, is this remainder a term, and we need to bound this error to find our accuracy. Now I need a theorem that will give me this error bound. Actually, we could check it from this figure that we see here. We see that this partial sums, as we said before, is alternating between terms that are decreasing. And now I know that this series has the terms b1 minus b2, assuming starting from positive, plus b3 minus b4 and so on. If I consider this is the first partial sum S1, if I'm going to add here a b1, then S2 will be subtracting b2, where b2 is less than b1, then definitely the S2 will be lying over here, greater than 0 and definitely less than S1, and so on. I'm going to add by B3 to this S2 to find my S3. S3 will add up to these sums, and I'll find it here. Actually, from this figure we will notice that the even numbers, S of 2 and actually is on the left side of the sums, and the odds as partial sums S2 and lying on this side. بالتالي these will converge definitely to a summation S. I know for definite that that the limiting value of my partial sums S must be bounded between two consecutive partial sums. Okay. Now if I took the limits as n tends to infinity as I'm doing the job, then definitely the sum will be bounded by these two. Okay. As from the previous graph, we noticed that S is bounded between two consecutive sums. Okay, and if we subtract Sn from both sides, we'll obtain S minus Sn greater than or equal 0, less than or equal Sn plus 1 minus Sn. Actually, we know that this will be plus or minus Bn plus 1. So and this will be our requested remainder term. So we know now that the absolute value of the remainder terms s minus sn must be bounded by the n bn plus 1 term, the absolute value of the n plus 1 term. Yeah, we will arrive at the following we will arrive at the following theorem. So now we arrive at this theorem that says that for a series that satisfies the conditions of the alternating series, condition 1 and condition 2, okay, the size of the error must be smaller than bn plus 1, which is the absolute value of the first neglected term. Okay, now let's solve this example. First of all, we need to show that the series converges. Let's check our condition. This is an alternating series that is written in the form negative 1 to the power n minus 1 phi 1 over n to the power n. If my absolute value of the nth term is 1 to the power n, which is definitely a positive value. Let's check the condition of the alternating series test first. The first condition about decreasing, we will notice here that 1 over n plus 1, I'm comparing the n plus 1 term with the n term. Definitely here the denominator is bigger than this, it will be less than this, but it is a decreasing sequence. Okay, second thing, our second condition, we must check the limiting value of this nth term, 1 over n to the power n as n tends to infinity. Now I have here power, which is a function of n also. Better write it in the exponential form, 1 over e to the power n ln n, like this. Better to be able to apply the limits. And I know that ln infinity is infinity and e to the power infinity is infinity. 1 over infinity is a 0. That second condition satisfied. Okay, checked. I can apply the alternating series test, and this series definitely is convergent, and it is convergent from the alternating series test. Okay. Now in the second part of the problem, we need to find the sum of this series accurate to 3 decimal digits. To have a feeling of how many terms I'm gonna add up to obtain this accuracy, in my approximation, I'll write the sum using the first few terms of the series. When I plug the 1, I'll have here a 1, plug a 2, you'll have negative 1 over 2 squared, and so on, okay? But these are the few terms that will construct my approximation for the summation. I don't know where am I going to stop, but I know the condition that is given, that I need the remainder term be bounded by I need the sum to be accurate within 3 digits, then the error term must be bounded by 0.005. This will guarantee that I have a 3 digits accuracy. Now I have this constraint of this formula. What is the value of n? We know for alternating series that the remainder terms are bounded by bn plus 1. So we will make some observation and look at our terms. If we looked at the terms مثلا 1 over 4 to the power 4, this is the term 4, b4, we will find that b4 is equal to 0.0039. This is definitely won't satisfy the requested accuracy. Let's try the other term, b5, 1 على 5 to the power 5 will have the value 0.0032. Definitely this is less than the requested accuracy, which is 0.0005. But then I'll stop at this before this term, and we will say that the remainder R4 is less than or equal B5. Okay, thus we will sum up our series up to S4. But these terms will guarantee the 3 digits accuracy. Now let's use the calculator to find our values. Now we know from the previous analysis that we're gonna add up to the 4 terms with the remainder term less than or equal b5, which is equal to or less than 0.0003. Okay, adding up the terms using the calculator, we arrive at this value. We know for definite that the first 3 digits 0.783, these are accurate, and these two digits actually we're not sure about. And the analysis done ensures that we have a summation which is equal to 0.783 correct to 3 decimal places. Okay, and by the alternating series theorem, we know that S minus S for absolute value is bounded by now B5, and this B5 actually is less than 0.0003. Okay.